the Croute method. This is similar to the Unital method, but the main difference is that here we have diagonal equals to 1A upper matrices. Okay. Now you can see that I have written almost everything on the board just because that we want that we emphasize on concept rather than writing on the board. So just cope up with me. We will start from left, and let's see that we have this set of equations, and as we know that we solve linear equations like this. We have an equation A x equal to B. A is the complete matrices, x is the variable matrices, and B is the constants matrices. Constant vector actually, but x is also the variable vector. We break A into L and U matrices like the algebraic position is. So here, and then we solve that Ux equal to B. This is the supposition. Obviously, U into x gives us a vector, a new vector that we have called B vector. And then we have LV equals to B. The let's say the algorithm of the problem will be that we will solve LB equal to B first, and then we will put B into equation 1 and solve for x. Okay. Now just leave this portion and come over here. That I have written step number 1. First, we need to find Q and L matrices. Now there is a method that we call Gauss elimination and Gauss-Jordan elimination and Gauss elimination. But these are the hectic methods. This is a little bit easier and let's say easier to understand method. In this method, what we do that we know we need to get U matrices somewhat like this, in which diagonals are 1, and the lower matrices is somewhat like this, in which diagonals are not 1 but any other number. Okay. And we know LU equals to B, since this is the breakup that we have done by ourselves. So what we do that we multiply L into U and we try to get A matrices. This is the case, or this is the requirement. What we did that we multiplied U vector and L vector in an order that L into U. So we have multiplied L into U. Do not confuse with this writing. Okay. So after multiplying L into U, we get this general matrices. In this, these are the variables. We need to solve these equations simultaneously. These are 9 different equations, for which this and this we know. Similarly, by matrix equivalency, 1, 4, 1 and 2 are equal to this column. Since there is only L1, L2, L3, so these are the directly the values of these variables. This way, when we solve this simultaneous equation, and let me show you some steps of this process. Like since we know that these are straightforward. Similarly, now let me solve it for U12 and U13. What will be the equation of U12? This will be 1 and this will be 3. Now this is an equation. This is an equation. These are all equations, different equations. We need to solve this equation. Let me take this one equation and I have written it like this. U12 is equals to 1 upon L11. What is L11? It is 4. So it becomes 1 upon 4. So we get U12 equals to 1 upon 4. Similarly, for U13, it is equals to 3. This L11 comes down over there and it is 4. So what we have is 3 upon 4. U13 is equal to 3. Similarly, let us solve this one here. Now we will have to select what equation to solve first. Let's say if I had chosen this one to solve first. How many variables do I have over here? I don't know L22 and obviously I don't know U23. So I cannot solve this. But here I have L21, I have U12 from over here and L21 from over there. since I only don't know is L22, so I can solve this equation, and as we solve it, L22 is equals to 5 minus L21 into U12. Since we know L21 and U12, it is 5 minus L21 from over here, which is 1, and U12 from over here, which is 1 upon 4. Okay. When we solve this, we get L22 equals to, obviously, 19 upon 4. Obviously, you can always recheck this. Okay. Now, with this similar process, since we now know L22, which is the second unknown in this video, now we only the only unknown is here is U23. You can solve U23 with a similar method. Then you will come over here. Now here we know L31, here we know L12, since from over here. So we don't know is L32. So we can solve L32 from similarly we could have done this before this, obviously. So you have to go. Let's just make it a general plan or algorithm that you have to come like this. Obviously, since if you do not do this, then you don't have U23 if you solve this first. So it needs to be go somewhat like this. Let me show it a little more like this. This. Okay. So it kind of inverted S. Okay. Now let's just, since now we similarly we get by solving this, I have done this before, so we know all these variables, and let me show you the gain values of L and U matrices, triangular matrices. That is 4, 5, 2. Okay. Now we have these all some U and L matrices. Now we simply solve these equations, and it is simple calculations that you can do it in calculators. And you have to calculate the U inverse to get X. First, you solve V by taking inverse of L and dividing it by dividing V by this L inverse, like somewhat like this. V is equals to V is equals to V upon L inverse. So you can do this, always do this. Okay. So this is going to be the Croute method. This method is used to solve the simultaneous linear equations. The set of equations we have is x minus y plus az equals to 1. Okay. So this method it requires to the breaking of the coefficient matrix, that is A matrices, and since we know the simultaneous linear equations are solved by this method, this A matrices is the coefficient matrices, B is the constants matrices, and X is the variables. We break the A matrices like this: L into U. L is the lower triangular matrices and U is the upper triangular matrices. The equations we get then are L U X equals to B. We derive Ux equals to V, and therefore L P equals to P. So the lower and upper triangular matrices in the two little case are like that. The diagonals of the lower matrices are all ones and U are the general numbers. Now, what we will do, as per the general rule, we will multiply this LU to get the A matrix. Like we will solve this equation, A, and then we will compare the elements of A equals to LU. Let me show you how. When we multiply L into U, we get this matrices. Now this seems to be general numbers thrown into the matrices, but believe me, there is a unique sequence in it, and I will show you when we will program this thing in MATLAB. Okay. For now, this is it, and now as I said that this tends to be equal to A matrices. So let me show you how, and let me demonstrate that. This thing is equal to A matrix. Okay. Now this. Now what we will do that, since we said that these two are equal, then by the general matrices rule we will say that U1 is equals to 4, this is equals to 1, this is equals to 3, this is equals to 1, this is equals to 5, this is equals to 1, this is equals to 2, this is equals to 8. Okay. Now these are simple linear equations that we can solve simultaneously this also this can be done in MATLAB, since I said that this has a unique sequence, that is a programmable sequence. So we can put this into the MATLAB. For now, we will solve it by simultaneous equations, and after the solution we get LU matrices. Actually, from here, since this is L, this is U, this is L, this is U. So what we'll do that we will find L's and U's values from these equations, and we will generate these two L and U matrices. And after doing simultaneous equation, the solution of these equations, we found L equals to. Let me update that. For better visual, or let's just let this. Now, by the simultaneous equation solution, we get now this is the solution. Now since we have our L and U matrices, we will simply solve these equations. That is, we will first solve, and we will calculate B from here. Then we will solve we will first solve this one equation, and then we will solve this equation. From here we will get B, and then we will put B over here and find our X. This will be the answer. Okay, and the next step will be the MATLAB solution. Okay, thank you. Assalamu alaikum everyone. Now we will study the curve fitting. One of the method of curve fitting. This is by the polynomial curve method. So curve fitting. In this method, what we do that we form a second order. Usually, it can be of any order, but let's say we will solve by second order polynomial, that is quadratic equation. And that quadratic equation is what? Y is equal, that we all know is n1 plus For curve fitting, we all know that we must have some data points, right? X. Now these data points are, let's say, 5, 7, 4, 6, 7. The first step here will be that we will form a table. Now this is not a necessary thing, but usually it's quite helpful, and most of the people do it like algorithm. Sorry. This is 1. This is X. Since S denoted by the notations, we have to put values over here: the x squared, x cubes, the x4, the x into y, and similarly. So let me do it fast, quickly. 5, 1 to 5, 6 to 5, 49. 343 and 240. Okay, now over here we have 16, 64, 256. Similarly, over there we have 30, 56 and 12. Over here we have 150, 392 and 48. Okay. Now we have summation for all these columns. We have summations written in a row, that is now all this thing is actually what we get from here is that y. Now we will form 3 simultaneous equations, since it is a quadratic equation that we are trying to form. So this general notation needs to be followed, which gives us 3 simultaneous equations, which are somewhat like and a0 And similarly, since it seems to be forming a matrix equation of Ax equal to B, so what we do, we will form this thing. Now I will write the augmented form of A and B somewhat like this. Okay, 3, 1, 6, 19, 1, 6, 19, 18, 19. What are these things? We call it B, and it is all these values. as I can show you. 70, the summation of f, summation of y, 98, summation xy, and summation x square y, 590, 590. Okay, 590. And these are the coefficients of this matrix. Now, what are the variables over here? Variables are a0, a1, a2. Variables are a1, a0, a2, and the coefficients are like over here. N is the coefficient, n is number of terms. Here we have 3, so I have written 3. Here the coefficient is summation x. Summation x is 16, so we have 16. Summation x square is 90, so we have 90. Similarly, we have filled over all these values in this matrix. Now what we will do is that we need to solve this, and this has equals to, sorry, now this is augmented matrix. So we know that when we have an augmented matrix, we simply write a0, a1, a2. And solving this augmented matrix is very much easy. It is by reduced echelon form that we have done earlier. So let me just write up some values over here. That is one. Obviously, the solution of augmented matrix reduced echelon form seems somewhat like this. Now it's very easy to reduce that a0 is equals to 20 minus 22.3, a1 is equals to 9, and a2 is equals to minus 0.667. Now we have our equation back. We can have our equation back. That is, this is the polynomial equation for solving the curve fitting problem, and which comes out to be minus 22.33 plus 9x minus 0.667 x square. Now we can simply put x values from this table and you will get the y variable. This method is an approximation. You will definitely have some error, but it's proven to be relatively good when you have data points that can be approximated by quadratic equation. Now you can have cubic equation, you can have fourth power equation, so it can go on so on. So that's it for today. Thank you.